আর এই ইউটিউবেও দেখছি অ্যাট এ টাইম, মানে সব জয়েন করছি।
আচ্ছা আচ্ছা, কতজন করলো এখন পর্যন্ত ইউটিউবে দেখতে পাচ্ছি?
ইউটিউবে দেখছি, হ্যাঁ এখন অব্দি 11 জন করেছে।
আচ্ছা, ইউটিউবে
আরো করছি আর কি। হ্যাঁ হ্যাঁ,
ঠিক আছে।
মিউট করছি। হ্যাঁ
হুম হুম হুম।
Good morning, sir. Good morning, sir. Hello, am I audible? Good morning, sir.
Yeah, good morning.
Welcome, sir, in today's session. Good
Yes.
morning to all the participants. Good morning to all the dignitaries here. Our today's distinguished speaker is Professor Dr. Shivaji Chakraborty. Welcoming you all to the fourth day of the Faculty Development Program on Research and Technical Challenges in Energy and Power Systems. I would take the privilege of reading out some of the outstanding achievements of Professor Chakraborty before the session is started. Professor Chakraborty is a full-time faculty member of Electrical Engineering Department of Jadavpur University from 1985, where he is currently Professor of Electrical Engineering Department, and he is presently on leave, and he is the Director of NIT Calicut. In 1984, he worked at the IISc Bangalore, India, as Indian National Science Academy Visiting Fellow. He did postdoctoral research at the Technical University Munich, Germany, as Humboldt Research Fellow in 1995, 96, and 1999, respectively. In 1998, he served as development engineer in the power transmission and distribution department of Siemens AG in Berlin, Germany. He further worked as Humboldt Research Fellow in ABB Corporate Research at Ladenburg, Germany in 2002. He was US NSF guest scientist at the Advanced Research Institute of Virginia Tech, USA in 2003, AVH guest scientist at the Technical University Hamburg, Germany in 2005, and again at the Technical University Munich, Germany in 2007. He has published more than 105 research papers to his credit, including 66 papers in IEEE Transactions and 26 papers in referred Indian journals. He was the chairman of IEEE Indian Council for 2017-18. He has one US patent, two Indian patents, and two software copyrights to his credit. He has authored 3 books and edited 3 books. He has developed 3 online courses on numerical electrical computation. He is a fellow of the Indian National Academy of Engineering, National Academy of Sciences India, senior member of IEEE USA, fellow of West Bengal Academy of Science and Technology, fellow of the Institute of Electronics and Telecommunication Engineers, and fellow of the Institution of Engineers India. He was an associate editor of IEEE Transactions on Dielectrics and Electrical Insulation during 2014-18. He was the chairman of IEEE Kolkata section during 2011-12, chairman of its power engineering chapter during 2003 to 2006, and the founder chapter of its Dielectrics and Electric Insulation Society chapter in 2012 to 2015. In 2001, he was the vice chairman of IEEE India Council. He was the ACS Pacific West representative of IEEE Power and Engineering Society in 2008, the global chapter secretary of IEEE PS in 2013-15, and the global ATCOM member of IEEE DEIS for 2016-17. He is an IEEE member and Energy Society Distinguished Lecturer since 2005. He was a member of the Court of Jadavpur University during 2006 to 10. He is a regular referee for many international journals like IEEE Transactions of Power Delivery and on Dielectrics and Electrical Insulation, IET Proceedings, etc. He is the recipient of Technical University Munich Ambassador Award in 2013, Technology Day Award from All India Council for Technical Education in 2003, and the Outstanding Chapter Engineer Award from IEEE Power and Energy Society in 2007. He is also the recipient of several other awards like the Jadavpur University Gold Medal for standing first in order of merits in both bachelor's and master's examinations, the Pandit Madan Mohan Malaviya Memorial Medal of the Institution of Engineers India in 1995-96, the Indian Ministry of Energy Department of Power Prize in 1994-95, and the third Millennium Medal of IEEE Calcutta section in 2000. He is actively involved in several sponsored projects funded by DST Government of India, US NSF, AICT, MHRD Government of India, and the World Bank. His current fields of interest are high voltage field computation, condition monitoring of transformers, optimization of high voltage systems, and lifelong learning techniques. Sir will be delivering today his topic on non-invasive monitoring of transformer oil paper insulation. And sir, you are requested to start your session. And presently, 75 participants have already joined in the YouTube session, and more are still joining. So,
So first let me have my presentation.
Hello.
So now you can see the presentation.
স্যার আমি তো পাঠিয়েছি স্যার আমি তাহলে পাঠিয়ে দিচ্ছি এক্ষুনি হ্যাঁ শেষ হয়ে গেছে শুরু হয়ে গেছে হ্যাঁ
Yes, sir, we can see that clearly.
You can see it. Okay. Okay, so let me start the session. As you have seen that the title is Non-Invasive Monitoring of Oil Paper Insulation of Transformers. Now I start with this statement that transformer is a very expensive equipment of our power system. Now when I state this, probably many participants may not be able to grasp it, that how expensive it is. I can give you a thumb rule. I think you know thumb rule. Thumb rules are not proved, but over the experience, people know that it works. So that
আমি ইউটিউব
power
স্ক্রিনে দেখতে
engineer,
পাচ্ছি না কেন
is it not visible, my slide?
yes sir it's visible yes sir it's visible
So, this power system equipment, there are many equipment, but transformer is the most expensive equipment. And the thumb rule says that if you take any substation, electrical substation, there will be so many equipment. You make an Excel table, you write down name of all the equipments, then put the price of all the equipments, and take the sum of all the equipment, then the transformer cost will be more than 50% of the total cost. So you can understand how expensive this equipment is. And that is why people are very, very focused on this particular equipment and its life, extension, protection, etc. Before that, before I start the whole thing, let me tell you a short story, what I had experienced long time back. When I was working in Germany in ABB Corporate Research in Heidelberg, I met the chief transformer designer of ABB. As you know, ABB, Siemens, these are the companies make the largest transformers of the world. And that time I was teaching transformer, etc. at Jadavpur. So I asked him a very simple question, that when you get the order for a real big transformer, and I am not talking about 10 MVA, 20 MVA, very big transformer, how do you start the design? Then he said that yes, when I get an order, first I appoint a photographer. I was thinking that, is he joking with me? What a photographer has to do? Then I asked, why photographer? He said, look, you have to understand that this is a real big transformer. It will be manufactured at our workshop, but finally it has to reach the party's site where it will be installed. Now, how it will go there? Let's say it will go by road. Then this photographer, what he will do, he will start from the gate of my company, factory, workshop, and drive to the party's site through all possible roads through which it can go. And it will take photograph of every turn, every overbridge, every railway crossing, whatever is there in that road. And then he will submit the report to us. We'll sit down, see all of that, and then finally we'll decide what is the maximum size that can be transported from my factory to the company party's side. And then we start designing, because size cannot be more than that. Otherwise, it will be, we can manufacture it, but it will remain in my factory. It will never reach the party's side. That was a shock to me, because I have never thought about this angle. I remember that when I was teaching all these transformer, etc., this design we start with, efficiency, flux density, core loss, copper loss, voltage regulation, so many things. I think you people are also doing this. But I never thought that this can be a constraint. So then he showed me a couple of photographs. So I will show you one photograph that will make you understand that what I am talking about. Now, if you see on your screen, this is a transformer. This photograph is not ABB. This is given by my Siemens friend. This transformer is now being transported through road. Just see the transport. And can you make out where the transformer is? It's not on the wheels. You see in the middle, just behind that car. It is practically hanging. It is not touching the road. And this is being pulled and pushed from front and behind by those wheels. Now I have a very simple question. If you look at this, do you think that this vehicle can take a 90-degree turn? The answer is absolutely no. Similarly, this height of this thing, now when you are going through this road and you find that there is an overbridge, you have to go under it. And if you find that this is touching the overbridge, will you have to break the overbridge? That is the importance of what he told me. That first I decide that what is the size of this transformer. Forget about efficiency, forget about voltage regulation. Given this constraint, now you design. You choose any material, anything, but size cannot be more than this. So that opened my eye on that day, that there is so much to practical life that we don't understand probably in our educational institutes, particularly in India. So therefore, the next point is you can understand how much will be the cost of this one. So we are here talking in $1 million. We are not talking in $1,000. So when this is installed at some place, it is almost mandatory that we have to be extremely cautious about his life. Why? Because forget about this transformer. I give you a very simple Indian example. It was about 5 years back. I discussed one thing, that a 50 MVA, very small one, not a large one in Indian scenario also. And 132 kV transformer, again not the biggest one, we have much higher voltage levels. That 50 MVA 132 kV transformer 5 years back, one company told me that its cost was 3 crores. 3 crores. Now if you consider a 400 kV transformer and 200 MVA transformer, that will go up to say 15 crore to 20 crore at least or more. Now you tell me, does anybody keep such a transformer in a godown? Answer is no. No power company has that much of fund reserve that they will keep it in godown. Second point is, if it goes wrong, the transformer is faulty, can you go to the market and buy one more? The answer is no. It's not a laptop, you go and buy it. You have to give an order that will be manufactured. Manufacturing time will be 5 to 6 months. After that, you will get it. So it is almost imperative that we have to protect this transformer against faults. Now with this backdrop, this presentation is, but before that, when I am talking about the transformer, first thing I have to mention that in any transformer, there are 3 types of material used. One is the conductor, second is the magnetic material, third is the insulation. Conductors are generally copper or aluminum, that means metal. Magnetic materials are generally steel, again it is metal. So these two are very robust material. This copper, aluminum, steel, they don't deteriorate all that easily. Whereas the insulation, that is primarily oil and paper. And there may be some polymers. But if you look at it, all these are organic materials. And organic materials are subject to aging. So when it will be used for a long time, its property will definitely degrade. Now, oil is one of the important insulation. So where this photograph I am showing is, this is called oil drain valve. All our young participants, I think you should always see a real life transformer. These oil drain valves are mandatory for transformers. Generally, this green color valve, you can see this will be closed so that oil will not come out. But for any reason, if we want some oil sample to be taken, it is very simple. We will open this valve and just like a tap, we will collect the oil and again we will close it. So we don't have to switch off the transformer also. The transformer can be running, but still we can collect the oil sample. This is extremely important from our monitoring point of view. So this is one insulation that we have. And the second insulation is the paper insulation. By the way, let me tell you that forget about all this equation, etc. and so on. But paper is a polymer. This we have to understand. And when we say polymer, very basic chemistry which students learn in the school level, it means that there is a monomer which is the basic building block, as you can see in the photograph also, and this kind of at the bottom of the slide, that these are the individual building blocks which are connected by a oxygen bond. What is this building block of paper insulation, which is called the monomer? It is glucose. So generally, when we ask anybody that paper is made up of what, the answer is cellulose, which is correct. But cellulose is the polymer. Its monomer is glucose. Now, I jokingly many times say that sometimes you will see that the cows are eating newspapers on the street. And we generally say that the cows are fools. They are eating newspaper. But please remember, nobody eats anything without any reason. Because these newspapers are made of paper, that means cellulose, that means glucose. That is why cows are eating that. So nobody is that fool. But this paper degrades over time. And this is a transformer winding where you can see that what you can see here is the paper. Inside you have the copper or the aluminum strip, which is covered by paper. This is called either single paper coating or double paper coating, whatever it is. And then you can see these small things. These are called press board spacers, so that there is a small space between the individual discs. This is required for oil flow, otherwise there will be very poor cooling. This is a typical winding diagram. But then you can see that the major insulation here is the paper and the press board, which are again organic material. So now we have to see another important result. On the left-hand side of the screen, it's a survey done in 2009 by SIGRE. As you probably know, SIGRE is the world's one of the top body of power engineering. And this says that it is in a British power utility, how many transformers were installed in which year. So you can see that the peak is around 1965 to 70. So many transformers were installed. Similarly, on the right-hand side, you can see it's a Dutch power utility in Holland. And again, you see the peak is around 1970. That is because that is the time when the big push was there over power engineering in the Europe. What is the scenario in US? Again, you see that during 1972, 74, there is a very big number of transformers, almost 180, etc. GVA. That is the capacity that was installed. Now, you can always ask, what is the Indian data? Unfortunately, Indian data is not readily available. We are so very sensitive about our data that we don't publish our data. But looking at this and looking at the Indian power sector also, because in Indian power sector also in the 1970s and 1980s was the big push when the power entire infrastructure reached the entire all parts of India. The question is very simple, that all these transformers which were installed in 1970s, are they all now discarded from service? The answer is no. Probably more than 90% of them are still running, although their age will be today almost 50 years. And here I must say that every equipment has a design life. That means the designer will say that what the life expectancy is. Transformers are typically design life of 25 years or maybe 30 years. But these are way above their design life. So what to do with that? But the question is, if every year a company has installed 200 transformers in 1970s, can we replace 150 transformers or 200 transformers every year now? The answer is no. Because it is very, very high cost, as I have already told the expenses. No power company has that much of fund reserve again. So what is the solution? Solution is that we have to first test this transformer. And here I am talking about the real life test, nothing to do with any simulation or anything. We have to do real tests and find out what is the condition of these transformers. If it is good, then we will not do anything, let them run. If we find that one or two transformer is in bad condition, then those one or two will be definitely replaced. This is the policy followed nowadays, not only in India, but all over the world. Then if we look at the failure modes in the transformers, if you look at the left-hand side diagram, it's a study in South Africa, where you can see that what are the different failure modes. And you can see that the largest block of the pie chart is aging. And when you talk about aging, it is the insulation. And on the right-hand side, if you see another study done in Russia, here the a large chunk is written as contamination of insulation. By the way, contamination not necessarily by the external contamination. It could be the result of aging. And here again, you can see insulation aging stated separately. So if we take these two, it is almost 50%. So it is quite obvious. And then there is core insulation failure also. It is quite obvious that insulation is the primary weakest link in the failure of the transformer. Then I was talking about the age of the transformer or any equipment for that matter. Now, this age, first of all, you have to think that how this aging occurs. Now, this aging occurs, of course, due to insulation deterioration. Then if it is a mechanical part like a motor, then because of rotation and others. And some cases like cables, erosion of metals. But we are not talking today of motors and cables, so we'll confine ourselves in insulation. Now, if I ask what is the age of any one person, what will be the answer? It is the difference between today's date and the date of birth. This is called natural age. But have you noticed that somebody who doesn't have good food, works 12 hours a day, then at 40 years, his health condition, and another person who have very good nutrition and works 8 hours a day probably and has a smooth life, at 40 years, his condition will be different. Now, this is The same for equipment. If you take any equipment which is used at a place where on an average the temperature is say 28 degrees centigrade, and another place where the on an average ambient temperature is say 45, then these two equipment after 10 years of service will not have same condition. So this is called functional age of the equipment. So when we consider the monitoring of the transformer, we don't consider the natural age, we consider the functional age. So we take many factors, for example, operating condition, environmental condition, very importantly, the loading history, that is the usage history. Some equipment works at 50% load, some can work at 90% load. Their age, functional age will not be same. So deterioration status depends on all this. So we have to keep all this in mind when we talk about the monitoring. Now, if you look at this maintenance or monitoring concept, it has gone through a very sea change. After the Second World War, this concept of periodic maintenance came, that we will maintain everything after a certain period of time. For example, if it is a circuit breaker, we will say that after 1 year we will test all the contacts. Now here the interesting point to note is that we are not bothered about the condition. After a certain time or a certain number of operations, we will do the maintenance. This is called periodic maintenance, or some people call it time-based maintenance. This concept changed in 1980s. We went into the condition-based maintenance because people understood that simple time-based maintenance is wasting money. Because if maintenance is not required, why should we do maintenance? Please remember, maintenance means cost. So condition-based maintenance means first we have to do some test. If the condition is good, we will not do anything. If the condition is questionable, then we will do the maintenance. But after 2000, another concept of maintenance has come. This is called reliability-centered maintenance. By the way, let me tell you, this maintenance in engineering is a very underestimated term. Maintenance, people think that you take one screwdriver and one plier and go and do something like a normal mechanic. The thing has changed dramatically. Today, maintenance is a high investment and high return of cost, return on investment issue. Reliability-centered maintenance means that not only the condition, we will also consider which part or which equipment has the maximum effect on the reliability of the system. Those which have maximum impact on the reliability, that will be maintained always at first. Because if something goes wrong, the entire system goes wrong. And if something is not so important for the reliability of the system, then we can do time-based maintenance. That after 3 years we will do something. By the way, this reliability-centered maintenance was not started by the power engineers. This concept was started by the aviation industry. Because you know the aircrafts, for aircraft condition, etc., forget about it. The 100% reliability is required. There is no question of anything going loose. So this Boeing and Airbus and all these companies, they started this reliability-centered maintenance. And after that, immediately the automobile industry picked it up. So all the big automobile companies, and Toyota is a leader in RCM, they started this maintenance. Now if you ask what is the power engineering scenario, it's very poor. Power engineers being very, very conservative in their approach, they are still not going through the reliability-centered maintenance. So we will talk about only the condition-based maintenance. Now when we talk about the transformer insulation, one of the tests that people are doing for last 70, 80 years, I must tell you, this is called polarization index test, or we simply call it PI. You ask anybody working in Calcutta Electric Supply, West Bengal State Board, any engineer will tell you that what is a PI test. This is very simple, done by an instrument called Megger. So you take that instrument, measure the insulation value at two different conditions. First, at 1 minute and then at 10 minutes. Now, we will get two readings. Now, typically, when you connect the Megger to an insulation or any equipment, generally a certain voltage is applied, DC voltage is applied to the equipment. It could be 500 volt to 5000 volts. So when a voltage is applied, the insulation gets charged, and when it gets charged, the charging current gradually decreases, and it measures the voltage applied and the current and then divides to get the insulation resistance. So it is quite expected that current at 1 minute will be higher and at 10 minutes will be lower. So if we divide the 10-minute insulation value by the 1-minute insulation value, it will be greater than 1. So this is a table which is given by Megger actually, that for a transformer, if it is less than 1, it is very poor condition. If it is 1 to 2, it is questionable. 2 to 4 is okay. Greater than 4, good. But once again, all the participants, if you talk to any power engineer, they will tell you that for a real life transformer, this 2 to 4, etc. is never achievable. And you will not get it. Mostly you will get it between 1 to 2. And then we have to take a very expert decision that whether it is good or bad. And this test is being done for last 70, 80 years. And I must say that this is a quite reliable test. People are having very good results out of this. But after that, I will talk about that how the paper deteriorates. One of the most important aspects that was found in 1920s, that moisture is the most detrimental part of the insulation, particularly paper insulation. By the way, let me tell you, oil, if it gets anyway deteriorated, we can change the oil. But if paper gets deteriorated, we have to change the entire winding, which means it is 50% of the transformer cost. So people are less bothered about oil, people are bothered about paper. Then in 1942, a very good paper was published. So you can see even in 1942, this research was done, that how moisture content affects the life in terms of its mechanical strength, etc., etc. And mechanical strength means mechanical strength of the paper, not metallic parts. And the best paper is 1969 that I found, that was published, that how this thermal aging of paper is related to its moisture content. This is a little bit of history, but then all these studies, they did one thing, that this entire insulation is divided into 3 parts within the transformer. I am talking about within the transformer. One is called the thick insulation. This is about 50% of the total insulation mass. This is generally all the press board, all the other supporting insulating structure, etc., etc. So that contains of to 30% mass is called thin but cold insulation. Thin means because these are mostly the end caps, the small barriers between the disc, etc. They operate, important part is they operate at the bulk oil temperature. Now there is something here I must say, the transformers are quite big, so there is something called bulk oil temperature and something called the hotspot temperature. These hotspot temperatures are very close to the windings. Now this thin cold insulation is generally called the main storage of moisture. They store the moisture. And then the thin hot insulation, this is generally 5% of that. And these are typically the turn insulation or the coil. They work hotspot temperature. So we divided the entire solid insulation into these three groups. Then how the moisture builds up? One is the residual moisture. That means when the transformer was manufactured, we take extreme care, but still, in spite of all the heating process, etc., you cannot make moisture zero from the insulation. Typically, or rather at the time of installation of the transformer, high voltage transformer, the moisture content should be less than 5 ppm. 0.5% by weight. Generally, it is 0.3% by weight. Then ingress from atmosphere, it means that if the sealing of the transformer, because transformer has a top tank, it has oil drain valve, etc. So if the sealing is not good, then moisture will come in very low because of care. But all this said and done, what will happen if moisture is generated within the transformer? Nothing can be done. And that is actually the primary concern, that due to aging, moisture is generated inside the transformer. And then that remains within the transformer and damages all insulation. So what we are today talking about is that part of the moisture which is generated as a part of aging. An open breathing system, again for my participants, I want to say that the transformer has a breathing system. We have the conservators, breathers. Open breathing means that the oil in the conservator tank at the top, that is in touch with air through the breather, of course. In an open breathing system, it has been found that moisture can come in spite of you giving silica gel and everything, whatever you have learned in your life. It will be around 0.2% by weight per year. So that means in 5 years, that 1% by weight, that much of moisture can come in. But that people have taken good care. Nowadays, all the high voltage, 132 kV or 400 kV transformer, they are membrane sealed, which means that top of the conservator tank is not connected to atmospheric air. There is a membrane, so moisture cannot directly come in contact with the oil. And in that case, moisture ingress reduces significantly. It is around 0.06% by weight. It is very, very significantly lowered. But if the sealing part I was talking, that top cover sealing or oil drain valve sealing, then lot of free water can go into the both membrane seal. Today we take very special care about that sealing. Now if you take the case of a transformer, then as I said, moisture will be generated inside this transformer. But then where will be this moisture? By the way, when we teach our students, we tell that transformer oil is hygroscopic in nature. And when we say hygroscopic, we say that if you keep transformer oil exposed to atmospheric air, it will absorb moisture. But the unfortunate part is that the paper insulation, that means the cellulose, its affinity for water is 100 times more than oil. So that means inside this transformer, what you can see, if there is a moisture and two material is trying to attract this moisture, one is paper, one is oil. And paper's oil, water affinity is 100 times higher. So it is quite obvious that most of the moisture will go to the paper insulation. And damage of paper insulation than the damage of insulation. That the whole situation is moisture is generated, then it is attracted by the paper, so it will go to paper and damage the paper. And then further moisture will be generated. So this is the entire process by which this very expensive equipment slowly goes towards fault. As I was telling that how much will be the moisture content, as in the second paragraph you can see that at the time of installation, generally it is less than 0.5% by weight in the paper and less than 6 parts per million in oil. This is the typically expected value. But as it is used, transformer is used, the moisture content can 3%, then we say this is the warning level. And at the bottom you can see that if it goes around 4%, then the condition is very poor. So what we are trying nowadays is trying to develop a monitoring or testing techniques by which we try to measure this moisture content in paper. This is I have taken this source is given. Now transformer winding on the right hand side, a schematic diagram, is a very big one. Please remember, it's not a small transformer like a radio transformer. So there is a significant height. It could be maybe 2 meters. So the question is whether the moisture content at the top and the moisture content at the bottom, will they be same? The answer is no. This study shows that 100% height, that means the top, 0% bottom. This is the moisture distribution. So at the top it is around 1%, at the bottom it is around 1.8 or 2%. This is for a particular transformer. Now here again another practical information we have to go through, that in a transformer, since it is a height is maybe 2 meter or more, is the temperature same at the top and the bottom? The answer is no. Because cold oil goes to the bottom. So generally, top oil temperature is high, oil temperature is low. And this temperature has a big role to play moisture distribution. I am giving you a practical example for all my participants. You will find it very interesting. This is a study done long time back, not today, in 1966. So you can find out that 54 years back. It's a 150 MVA 400 kV transformer at the first paragraph. Just look at that. This one transformer has 7 tons of paper insulation. Can you imagine? I think young people cannot imagine. You have never thought about it, that when you learn by drawing 2 coils that this is a transformer. Please understand that this transformer has 7 tons of paper insulation. Now, if I say that it has 3% by weight of moisture, so 7,000 kilogram of paper, 110 present in paper. Just try to imagine this. 210 kilogram of paper or water is present. That same transformer has oil 80,000 liters. So my dear participants, try to understand that we are talking about really, really big things. And if I say that 20 parts per million is the moisture content, which is quite high, and if you convert it into kilogram, it comes 1.6 kilogram of moisture in oil. Now that's what I want to highlight to all of you, that 3% by weight and 20 parts per million is not very bad, but it's warning level. But look at that, 210 kilo of water will be in paper and only 1.6 kilo in oil. That's the real situation in a practical transformer. And these 210 kilo of water will damage further the of paper insulation. Replace the 7 tons of paper insulation, practically it is half of the transformer cost. Generally, paper moisture is always expressed in percentage by weight. Oil is typically expressed in parts per million. Now, when I say parts per million, I always ask a very simple question. How do you measure parts per million? Do you cut that sample into million parts? The answer is no. It is very simple. Again, this fact to always keep in mind. Measurement that you take one and measure how much moisture is there. If there is 1 microgram of moisture in 1 gram of oil, bottom part if you see, it is 1 parts per million. So please remember that these are not very complicated. We get confused by the terminology and then we can't answer. This we have to explain to our students. And then the teaching becomes very interesting and students become very interested because see, if you tell them something which is available in a this the learning and experience. There is something called a moisture dynamics. Let me tell you my research in last 15 years when I was doing this condition monitoring. I found that what is called an interdisciplinary research. This research led me to this moisture dynamics, and then we found one fine morning that we are not talking about anything with Ohm's law, anything with any circuit theory, but we are talking about all the hydraulic laws, that how moisture moves. So then I understood that how this interdisciplinary research today comes into play. But generally this moisture migration, that means movement of moisture within the transformer, can happen because of concentration gradient. Concentration gradient happens when we generally replace the oil, then suddenly oil becomes already there inside and they already have moisture. So concentration of moisture in paper is high than the oil. So what happens? Moisture moves from higher concentration to lower concentration. Then pressure gradient. Sometimes we do the drying of a transformer with a vacuum pressure chamber. So because of that, the moisture comes out of the paper. This is migration. But these are all special. Either oil is replaced or transformer is dried. But what happens every day is called the temperature gradient. As the temperature goes up and comes, it has been now established conclusively that moisture moves between paper and oil. When the temperature increases, moisture moves from paper to oil. When the temperature decreases, moisture moves from oil to paper. The interesting part is that the time constant of these movements are different. The moisture moves from paper to oil at a faster rate, but from oil to paper at a slower rate. Now this has an important bearing. Now, this I have explained right. Now, two things have been experienced in life. There was a case when a transformer was, the oil moisture was found high. So the company decided that we will change the oil. So previously, before the change, it came down to parts per million. After 1 month, they thought that we will again test. And when they tested, immediately it's 16 parts per million. Now that because in one was understood that it is not the oil that has deteriorated, but because there were a lot of moisture in the paper and when the oil was changed, so concentration of and oil oil moisture. This is one real life example. Another example that was that many times has been found, particularly, give me an example that, let's say, some a transformer is working at a place where the outside temperature is minus centigrade. There are so many places in India and Europe and America. There are so. What happens is that the temperature is centigrade. The temperature of the transformer, because of the temperature. Generally, a transformer is designed for a temperature rise of maximum 65 degrees centigrade. Typically, at 80% load, it will run at a 50 degrees centigrade temperature rise. So even if outside temperature is minus 10, the inside plus 50 degrees centigrade. So everything will be fine. But what happened is that suddenly there was a fault and the transformer tripped. Now, the moment it tripped, what happened? Previously, the inside temperature was 40. So what has happened is that a lot of moisture has suddenly down very fast. But moisture cannot go back to paper from oil at that rate. So and as you know, density is exceeded, then it will not remain. So water is generated moisture, they were absorbed in the insulation, either oil or paper. But these are free water. Now water is oil, so what will happen? They will go to the bottom of the transformer tank. Then when the fault is in the transformer is started, and as the transformer is started, you know the cooling fans, they start fast. What will happen? They will draw the oil from the bottom of the tank and then through the cooling tubes back to the transformer at the top of the tank. So when the transformer starts again, these cooling fans draw the oil of the tank and then it will almost like a spray come from the top of the tank on the transformer winding. And the transformer winding happened many times. So people take adequate care nowadays. Now, what I want to say to my young friends who are participants is that, so when we talk about transformer, load loss, some magnetic flux, but it's not so simple. I remember when I was a transformer equipment, which are much more complicated. But later on, I have learned through hard experience that although it is a static, the most complicated. Now, when this movement of moisture oil takes this equilibrium, a lot of, as you can see from the top, starting from 1960s to 1990s, people tried to find out what are the equilibrium. The most famous woman's scarf. By the way, the woman is an Indian from Kerala. He moved to Canada. He is no more. This is the curve at different temperatures. So you can see from 100 degree to 0 degree. X-axis is moisture in two curves, solid curve and dotted curve. That means one is temperature decrease. And temperature decreasing always is slightly higher. And as you can see, let's say 0 degree centigrade, you can see that moisture in paper is much less, whereas uh, it's the reverse. 0 degree centigrade, moisture in paper is high, moisture in oil is said that when the temperature, moisture moves from oil to paper. Whereas you can see oil is high, is low, because now has moved from paper to oil. So how do we find moisture in oil? This is typically by a titration technique. We open the oil drain valve. This is called curve, but this generally oil value, and more give any specific oil value, it gives a overall value. Then how can we get the paper moisture content? One way is to find out through this curve that I have shown you, that if I know the oil value, I can get the curve. But then there is some problem here. What is that problem? That these curves are temperature dependent. Now, typically, if you look at the winding temperature and the top oil, they don't have the same temperature. So therefore, which temperature I should take? Generally, transformers, if you go and see, there will be two thermometers. We call it top oil temperature, bottom oil temperature. We take these two readings. We generally use that temperature. Now, here are two problems. First is this temperature distribution. As I here, it is not. Second is that these curves are only on equilibrium. Is there really an equilibrium inside the transformer? The answer is no, because temperature changes every now and equilibrium. So, in this process, if we do it 5D measurement, entire estimation of paper moisture. So, although this was an easy way to find the paper moisture, it doesn't work well. There will be some diagnostic techniques. So people have worked very hard. Now, whenever we do the test, first of all, we have to understand that are we trying to find out the local fault or the global condition? That means overall insulation condition. For example, if we are interested in effect, this second paragraph in green color, there are tests. For example, partial discharge test. Nowadays, frequency response analysis to find mechanical local defects. But if we do the oil analysis, as I have already explained, the one that I am going to explain is dielectric response measurement. They will not give you the local defects. They will give you only the global information. That means overall insulation condition. Dielectric response is that you apply a voltage to the current. It's very simple theoretically. Now, two types of measurements we do. First is called in time domain. That means we apply the voltage, frequency domain measurement. Here we do in a different way. In the first one, time domain measurement, we apply DC voltage. In the second one, the frequency domain measurement, we apply AC voltage. And we apply AC voltages of different frequencies. By the way, let me tell you here, there is no MATLAB involved. Any transist way. That means through connecting the equipment. Today I will talk about only the time domain because in one lecture everything cannot be explained. Engineers during minute and 10 minutes. But then the charging current is changing. It was measured and it was found and depolarization current measurement. Charging, then this next part is called volt DC voltage. Then after a given time, when the charging current becomes stable, and we measure the depolarization current. Current is not zero. The question is why? Insulation resistance. So this final value of so in the end, it's a conduction current. Whereas in the during the dielectric polarization current. And in the discharge part, there is no question of conduction. I'm not going into the equation today. This is for hardcore. So this circuit is very simple. On the left hand side, or rather first you see the test object. Now this test object can be this. Then when the switch is object, then we put an electrometer. We put the switch in. So it is depolar. Two questions come here. Capacitor, you will find it will come to the state. My experience, I have seen, and transformers even after 6 become stable. Then you can understand that how complicated. Average, I have seen 2-3 hours, and then another 2 hours get to measure. So the total time almost about is not done in equipment and that why I am saying to know what is it ampere measured of. But please try and it's a very noisy environment. Try to measure difference between simulation and so we need an electrometer which is a test object. So you can see one connected to the we don't connect. We short circuit the hand side diagram. Then in short circuit, it becomes a electrometer. So electrometer will be between these two. So then whatever the current, it flows through the winding and back. So you see, does not give local. For a single phase transformer, we measure earth and the bushing. I will talk a little bit. Very interesting. By the way, let me applying a constant, and I'm applied any DC voltage. Please do that. You will practical difficult. These voltage, it has to be constant, because if this, my dear young, understand that is quite will be a straight line. Yes, in RVM, what we do, we apply a voltage, but not for the full time. For polarization timing. So we are keeping is expected. We put a voltmeter across the transformer terminal. You will get a voltage waveform. That voltage will go up, will come down. I am getting it in this way. Circuit, we have a voltage. This is the sample which can will be, so it will be checked. Then the source will be disconnected. The switches will be closed. Then the switch 2 will be put to B. So everything will be open. Voltmeter is connected across the sample. So this is a very simple circuit. It can be done. So let me explain now what is happening. Typically, the equivalence transfer any capacitor means that I have a resistance and capacitance in parallel, and I have a voltage. Typical equivalent for a transformer. Now, what?
Sir, hello, sir.
Yes.
Sorry to interrupt you, sir. The audio for the past few minutes is continuously fluctuating. Can you check your internet connection, please?
My this is what I am using, even not Wi-Fi. It will be very difficult. So many times. I'll speak slowly so that this wave shape this will be exponential. if you put RC, so typically exponential branches in parallel added. So equivalent circuit, this RC branch, the insulation, etc. They are getting charged. Time to fully see. Initially, when we discharged it, so now if I open capacitors here, they were not, and it voltage for it will rise when the after that all this C0 and all starts decreasing. This is called the tools to find out the in our lab high voltage. We have developed this equipment, developed it in our the left hand side, and it was like, and then after seeing our results and our collaborative project with, and we have tested that we developed patients site after the laboratory. Found that there are all types of noise. And we put a filter. Noise. In series. That it gets changed. So your analysis gets spoiled. I tell you, this took us 2 years to solve. And but almost that we were doing pure. This is how we have learned in life. Giving is like not a good or 20 kV transformer. So we took say that your result is good or bad. No, they give, and then they give range. Who takes the decision? We thought that's the identified structure is there. Our tested result. Then we propose who owns this transfer, whether they will the overall thing is very simple. Of course, practical a main transients is the frequency of noise problem is greatly reduced, but that is a completely another domain of we have published a book. This is this book. Say that our team we have now more than 20 IEEE. This is my research team. It all started. And Dr. Vishendu, Dr. Deva, your program. University now, Dr. Rijit Paula, Kumar Pradhan. This is all these 6 people. Outstanding work in this area. Thank you. What is the time now?
Hello, sir.
Yes.
It's 11:16 right now. You were asking for the time, I suppose.
Yeah, I can give you some 10 minutes or so.
Yeah, sure, sir. Sure, sir.
Somebody has a question?
Yeah, yes, sir. There are questions already posted in the chat box of YouTube.
Tell me. Very.
Sir, shall I ask Madam to read out the question?
Yes.
Actually, sir, your voice is not coming clear. So that is why.
Some problem happened. Dedicated connection, but some problem is here. But
sir, shall I put on the questions? Hello?
Yeah,
Okay. Kamalika madam, can you please read out the question?
Yes, madam.
Okay.
Yes, madam. Yes, madam. Yes, madam. Well, first question, sir. Can we use mica as insulator instead of paper?
the mica cannot dry type insulation, not in oil paper. It can be used, but not. Next
question, madam. Next question, madam.
Yes. One of the audience has asked that please give us the scenario of solid state transformers and its advantages and disadvantages.
No, this is mistake. One is not the one. I am not talking about here power electronic device. I am talking about the conventional transformer with oil paper insulation. So I can talk about solid state transformer. I don't work on solid state transformers.
Okay, sir. So these two questions were there. Thank you, sir.
Okay, thank you.
Okay. Sir, sir, is it since the today's session was bit interrupted for the last few minutes? So one one of the participants have asked for sharing or PPT if it is possible. Hello, sir.
I will send
Hello.
it by email.
Okay, sir. Okay, sir. Okay, sir.
Okay, then.
Sir. Okay, sir. On behalf of the department, sir, would like to present you a token of appreciation from our end, and
Okay, then let us conclude it. Let us conclude the session then.
sir.
Okay, thank you. Thank you. I have seen it.
Okay, thank you, sir. Thank you. Thank you to all the participants.
Okay, I'm
Okay,
leaving.
thank you, sir. Okay, sir.